After we've agreed that a system has to be usable anyways, we move on to the next subsequent important factors which a user is very much mindful of. In this module, we shall cover what is scalability. We look at a simple scalability analysis and the connotations of scalability onto the network model. To put it simple, scalability is the ability to grow for a network in our case. Specifically, from the network perspective, scalability is the ability to grow or to add few things to it. These factors which may be added or extended within a network are: we can increase the number of applications on a network, the number of sites from where the users are accessing the data and other services, the addressing scheme which is used at each of these sites, the total number of users which are accessing the network services, and the number of servers which are providing services to the users. So a scalable system or a scalable network is one which allows all of these factors to be increased and extended with indefinite size. Now we look at the implication that arises when we make a system so scalable. So the cost that the network or the users would bear is in the form of the effects of the growth. The first one is, of course, efficiency. While designing a system, we must understand that as the network and the factors increase, the efficiency is going to decrease with the increase in certain factors. But at the same time, there would be certain factors which, if increased, are going to increase the efficiency. Another important factor that is affected by increase in size is the execution time. From a network perspective, the end-to-end time. The end-to-end time is going to increase with certain factors such as length of the cable, the number of devices, etc. But it will have an inverse effect if certain other factors are used. For example, if fiber optic cable is used, what if the switching fabric of a switch is used with very high backplane? In order to make our understanding of efficiency and the time it takes better, let's look at some basic expressions. First, let's make an assumption that the problem at hand or the network application present in a network is not changing much. So it means that we have to assume that the execution time is dependent upon certain factors, keeping other factors constant. Because if we assume everything to be scalable at the same time, it will give us an open-ended problem, finding a solution to which becomes very problematic. Here we see, if we want to develop the understanding of a system, we must look at the execution time as a normalized representation. Why do we say that we are looking at normalized way? Because normalization allows us to look at the overall performance gain or loss between two parameters of the same kind and having an effect on the third parameter. Here we see that the execution time as a relative entity is the ratio of the time it takes with one host and the time it takes with n number of hosts. So if, let's say, we have 10 hosts and the overall execution time for one host to 10 hosts is 10% or 0.1, it means that the execution time is fairly linear. But if the time for one host divided by the time for 10 hosts is giving us a value other than 10% or 0.10, say 0.05, it actually means that the execution time given to us in relative form is non-linear. Similarly, if we were to determine the speed that we get with increase in network size, the speed up factor, we look at the expression below, that is, the speed up factor is represented by S relative. It is actually nothing but a product of the number of hosts, say number of servers in this case, multiplied by the execution time for one host. So if we are looking at, let's say, one server, the number of hosts will be 1 and the execution time would be for one host. So we'll get S relative as equal to one server speed up. But if we increase the number of hosts to be equal to, say, 10 servers, in that case, we see that S relative is giving us a factor of 10. So this is the case when we are getting a speed up of 10 by including 9 additional servers. If we want to understand the execution time in terms of the other broken down times, let's look at this expression. This expression tells us that the scalability of the system is dependent upon the execution time, which, when broken down, is actually the computation time, the time it takes to communicate the messages, and the stall time when the system is not doing anything. The other expression is actually telling us the time it takes to transmit a certain message. The time it takes to transmit a message is dependent upon TS, which is the bootstrap or the startup time, which is more like y-intercept, and T sub W times L. T sub W is actually the overall transmission cost or the transmission time for a basic unit of data. When it is multiplied with the total data which is to be sent, and then it is added to the bootstrap time, this gives us the total time it takes to send out a message. Now, the expression above is the execution time, and the expression below is the time to send a message. Finally, when we look at what conclusions or impacts these would have on lower layers, we see that scalability affects the choices which we make in all the layers of the network model.